In this work, we propose a novel method of conditional image generation via multiple labels. Generative models have contributed a great deal towards the generation of photorealistic images. Starting from noise, these models can synthesize images from distant data distribution. However, users, such as digital artists, have little to no artistic control. On the other end, there is the rendering-based approach, where all necessary information is needed to obtain the final image. Here, the digital artist has full control over the content of the image. However, it's very challenging and time-consuming to achieve photorealism. In most cases, both extreme scenarios are not desirable, and a digital artist would want the right amount of control. This can be partially achieved by conditional image generation. In such cases, we start with an input label, such as a semantic segmentation, and feed it into a generator network, which will output the photorealistic RGB image. In this paper, we propose a different approach by using multiple input labels, such as normals, depths, and edges, to achieve more geometric control and generate high-fidelity images. We propose a label merging network, along with an image synthesizing network to generate the final output image. Two main challenges that we face when designing the label merging network is the heterogeneity and the sparsity of the input labels. Heterogeneity implies the different representation of labels, and the sparsity can arise through missing label annotations or by the label definition itself. To this end, we propose the transformer-based label merging network, short TLAM. This network consists of two parts. First, we project the different data types into a latent space, and then we combine them through a transformer encoder followed by an averaging step to obtain a single homogeneous feature embedding. Note that this process operates on a single pixel location. Repeating this process for all pixel location results in a tensor, which we call the concept tensor. The concept tensor is then the input to an image synthesizing network, such as SPADE or ASAPNet. The concept generation block learns the best representation of all the labels at a single pixel location. This approach solves the heterogeneity problem. When dealing with sparse labels, we add a mask indicating the missing pixel value and show that it can inherently take care of sparse labels. We conducted experiments on 3 different datasets: Cosmomy, Cityscapes, and NYU Depth dataset, each containing up to 5 labels. Presenting some quantitative results of our model, where we compared the FID on the Taxonomy dataset. SPADE and ASAP are state-of-the-art image generation network, which achieve an FID of around 72. Note that these models can only use the semantic segmentation as input, while our method uses multiple labels. We have constructed 2 baselines for the multi-label setting, the naive and the CLAM baseline. Our method outperforms both baselines in the sparse as well as in the dense setting, achieving an impressive low FID of 35. Qualitative results show that our model generates more realistic and detailed images. These details can be seen here on the ceiling structure or on the chandelier, for example. Similar results can be achieved on other datasets. In conclusion, in this work we introduce a new problem where we use multiple input labels to condition the image generation process. To do this, we propose a label merging block. We show that it can tackle the problem of heterogeneity and sparsity of labels. Our model can generate photorealistic images with more details, and as an application, this method can be used for geometric image editing. You can find more results and details in our paper and supplementary material.